Okay, thank you. Welcome. Welcome to the Agile Tour. As he described, I'm interested in software engineering as an idea. I'm a card-carrying Agile practitioner and have been since before it was called Agile, to be honest. So I'm a believer. But if there is anything that's post-Agile, I think it might be engineering. I think that at its roots, the reason why Agile is important and the reason that it works is it's kind of a craft version of engineering. And I want to talk a little bit about what a real version of engineering might look like to explore that today. So that's my topic for today. Let's get this working. There we go. So my theme really is that I want to talk a little bit about what engineering is as a concept. I want to talk about some common foundational principles, and I want to recommend to you 10 guiding principles for what we might call software engineering. And then I want to demonstrate putting those into practice a little bit to see how that affects the kind of code that we write, because fundamentally that's what it's about. This is really the thing that this comes from. I wrote a book on this topic called Modern Software Engineering. This is a blatant plug of my book, yes. But I really want to, in this book and in my presentation, I want to try and convince you that I'm not just talking about some label that we attach because it sounds more important. I'm talking about a practice that we follow. And if we follow this practice, I think that I can guarantee that you will get better results than if you don't. And that's what engineering ought to mean. That's what it means everywhere else. So why doesn't it mean that for us? So that's really my theme for today. I've got lots of slides, so I'm going to have to rush through, I'm sorry. In other disciplines, engineering is really just means the stuff that works. If it doesn't work, we change it until it does, and then when it works, we call that engineering. That's not how we tend to use the term in software. On the whole, my impression is that in software development, what we usually mean when we use the term software engineering is something that's overly bureaucratic and stupid, or it's something that's just an alternative phrase for being a programmer. You know, I'm doing engineering because I'm typing code. That's not what I mean. I'm talking about something more than both of those things, and neither of both of those things. So, software is difficult stuff to do, so we ought to find better ways of doing it. And I think that's what it is that I'm trying to talk about, what I'm trying to describe. So what is it that works for us in that context? One of the weird side effects of me talking about software engineering is that I get involved in lots of conversations about bridges. People come up to me and say, yes, Dave, that's all very well, but software engineering isn't bridge building, is it? And of course software engineering isn't bridge building. It's something else. I would argue that probably bridge building isn't bridge building, what we think of as bridge building either. But certainly I think that what we can say about engineering as a discipline is that it's different depending on the nature of the problem that we're applying it to. So bridge building isn't the same as house building. It isn't the same as automotive engineering. It isn't the same as chemical engineering or aerospace engineering either. All of these things are distinct, and all of them are about what really works in that context. And so that's one of the things, the implications of that is that whatever it is that software engineering is, it will be ours. It will be different to other forms of engineering. And there are some unique properties of the things that we do that make our version of engineering special to us. And I want to talk a little bit about those as well. What I'm going to do today is I'm going to pull out some examples, though, about general principles and use examples from other forms of engineering to try and put these into practice so that we can kind of make sure that we're talking about the same stuff. And I might mention some Lego as well along the way. So what does all of this mean for us, really? What is engineering, really? This is the definition that I came up with for my book and the definition that I tend to use. And I like this definition because it's short, succinct, and every single word here is important. It's the application of an empirical scientific approach to finding efficient solutions to practical problems. I think all of those words matter. If you take any of those words away, this is a less good definition. So I think that's a pretty good statement of what it is that I'm talking about. I think at heart, what it is that I'm trying to say here is that certainly in terms of the origins of the word engineering in English comes from something else. It comes from building siege engines, millennia ago, and those kinds of things, articles of war. But I think that in modern terminology, when I say engineering, one of the ideas that I think I'd like to plant in your mind, rather than thinking about somebody fixing your car, thinking about somebody building a Mars rover that's going to wander around on Mars. That's engineering that does that. And that's the kind of mental model that I'd like you to kind of hold. So I think that on the whole, when we talk about that form of engineering, what we're really talking about is the practical application of scientific rationalism. That's what I'm trying to recommend to us all anyway, the practical application of scientific rationalism. So to put it more simply, if you take that read on what it is that we mean by engineering is the way that we solve, as a species, it's the way that we solve hard problems. And one side, I chose these pictures with care. The woman there, the short woman next to the pile of documents, that's Margaret Hamilton. And she has a special place in the history of our discipline because she's the first software engineer. She invented the term. She came up with the concept of software development as an engineering discipline while she was leading the team that was designing the flight control software for the Apollo space program. So she's an important person in the history of our subject. I would argue that fundamentally what we're talking about here is really the foundation of our civilization. If you look around this room, pretty much everything in it is the result of some form of engineering. The lights that are above the stage, this box here is an engineered thing. It's measured and it was constructed in a certain way and all of these kinds of things. Obviously the computing devices that are putting out the information, all of these things are engineering structures. The clothes that I'm wearing are engineered. They're designed and the materials are created using engineering techniques. That's the way that our civilization works. It's the way that we do the hard stuff. It's the stuff that our culture is built upon. And just to try and put that into perspective, here's a graph that somebody else created of the advancement of technological things. And you can see that we've existed as a distinct species for people argue about it, but it's somewhere between 250 and 350,000 years. And for most of that period, in terms of technologies, as far as we can tell, it's a flat line. Then we get into the kind of the historical record, and we start to see some more things. And then something happens around here. It ticks up, and there's this explosive advancement. So that's when science was invented. And there's no accident that that's what happened when we started getting better, more rational ways of approaching problem solving. Here's another graph. This is based on the work of Buckminster Fuller, who was interested in the rate at which human knowledge was expanding. And he estimated, when he first did this, that human knowledge was doubling every few years. So in 1900, he estimated that the whole of human knowledge was doubling about once a century. By 1945, it was doubling every 25 years. By 1982, it was doubling every 12 to 13 months. And by 2020, IBM estimated, I'm not quite sure I believe this, but IBM estimated that the whole of human knowledge was doubling every 11 to 12 hours. So there's this explosive growth going on. So science happened back there somewhere, and computers were invented here. So our discipline is part of the reason for this explosive growth of knowledge. So my last part of defining what engineering is about, I suppose, is, so what's it really for? And I think this is one of the things that we, as a discipline of software people, tend to get profoundly wrong. So I think that what we tend to imagine is that the job of engineering is to give us the correct answer to things. I don't think it's that at all. I think it's much more like this. The reason for engineering is not to define the one true solution, the perfect solution that we're heading towards. There's no such thing. There are always a myriad of solutions. The job of engineering is to do this, is to identify the stupid solutions so that we don't do those, to rule out the dumb things, rule out the bad ideas. We're not going to put engines on aeroplanes underneath the wings like that, where they can touch the ground, because that might make them catch fire, and that might be dangerous. We're going to measure things carefully when we build bridges so that the bridges match up, the bits line up and they work. We're going to stop doing the stupid things. What is it that we can do to stop us doing stupid things? The other take on engineering that I think that we tend to get profoundly wrong is that we confuse it with production. We confuse it with the making of things. This is a reasonable mistake, but it's still a mistake. The problem with this as an idea is that we don't have a production problem. We are completely different. If you're making physical things, bottles, aeroplanes, donuts, whatever it is, if you're making physical things, the act of making that physical thing is complicated. And that's probably going to be one of the harder parts of the whole endeavour, whatever it is. But that's never, ever our problem. And it's not our problem for a kind of profound reason about the nature of software. Software is really crystallized ideas. So we're going to come up with some ideas, we're going to write those ideas down in the form of code that we can understand and share and kind of help us to organize our thinking. And then we're going to take that code through some kind of process to turn it into a stream of bytes. And we're going to end up with this big stream of bytes. And one of the unique properties of a stream of bytes, whatever it represents, is that given how brilliant computers are, we can clone that perfectly for essentially zero cost. So however big or complicated your system is, fundamentally for essentially zero cost, we can just press a button. Sorry, I was ahead of my animation. We can press a button and clone those things perfectly. That's production. So once we've got the stream of bytes, we can just churn out as many copies as we want for free. That's a unique of software development. So our problem isn't production. Our problem is coming up with the original stream of bytes. It's the design step. It's the thinking about and solving the problem. That's a different kind of thing to solve to production engineering. So when people build the equivalent of production lines, waterfall development, that's a dumb idea because that's assuming that we're building cars, not writing software. So engineering then, certainly our form of engineering, certainly the kind of engineering that I'm describing even when I'm thinking about new physical things, is all about exploration and discovery. It's about trying stuff out, seeing what really works, and keeping the stuff that works. That's what we're really looking for. So software development is all about learning and discovery. So that means that what we need to do to be able to be good at it is to optimize for learning. We should be world experts at learning. That should be the core, the root, the foundation of our job. And I think practically it is. I don't think we think about it that way around enough. And I think that if we did, we'd end up doing a better job. But fundamentally, that is what we do. Because of the economics of production being free for us, we are always producing something new. It might only be new in our context, but it's always new because we'd be stupid to do anything else. Because we could copy, if we've already got the answer to that thing, we could just copy it for nothing. So we're always producing something new every time. So we must be learning to be able to do that. But the other thing about software is it's complicated. And so the other part of this problem is that we must also be expert at managing the complexity of the systems that we build. So I would say that the two foundations on which we would need to build any discipline for engineering in software is that we must become experts at learning, and we must become experts at managing the complexities of the systems that we build. And those are the foundations of what I think of as software engineering. So for each of those things, I've got 5 ideas that I think are fundamental to our ability to achieve those outcomes. So if we're going to optimize for learning, we need to be iterative, experimental, feedback-driven, incremental, and empirical. Don't worry, I'm going to go through these in more detail and give you examples of each of them. That's the rest of my presentation, pretty much. And we'll start with iteration. So here is the Wright Flyer. This is the first heavier-than-air man-carrying aircraft. This flew in 1903 on December the 17th for the first time. And this is a photograph of that event. This was the first ever flight. Interestingly, the duration of the flight was shorter than the wingspan of a jumbo jet. But it was proper controlled flight for the first time. At this point in history, these things were death traps. And for the next couple of decades, nearly all of the pioneers of aviation were killed by the things that they were trying to pioneer with. It was a really dangerous thing to do at this point. So what happened next, or at least a little bit later, in kind of the iterative evolution of the aircraft, is something like this. This is probably the first recognizable passenger-carrying aircraft. This was around the time of the Second World War, so around 1940s was when this plane came into effect. And this was practically, we got people inside a metal tube and in comfortable seats and all of that kind of stuff, and the pilots at the front. All that might sound weird, but there were examples of all of those things where those things weren't true. It was a different layout what they were trying out. So they tried this, and then eventually, by the 21st century, we get to something like this. As an example of what that kind of iteration, slow, certainly, but what happened over that time is that by 2017, the commercial aviation flew the equivalent of 2/3 of the population of the planet, and nobody was killed that year in commercial aviation. That was remarkable, that advancement, but that's what engineering does. It might take a long time to iterate, or it might do it more quickly. But that's what iteration and our ability to change things and evolve them and make them better and better and better and learn from our use of those things. That's fundamentally what it is that we're talking about when we're talking about working iteratively. I think there's part of us, all of us, maybe less us agile people in this room than other parts of the industry, but there's part of us as a species that tends to think that thinking really hard about a problem and getting it right first time is the better answer. That's absolute rubbish. That's not what we ever do. So iteration is by far the more powerful way of achieving a result, an outcome. The amazing thing with iteration is that we can have some goal, and it really doesn't matter what the goal is. It can be anything. And all we need is to choose where we're going to start from, and then figure out some kind of measuring stick that we can use as a fitness function to determine whether we're getting closer or further from the goal. And then we start to iterate. We can even do this randomly. And this is how machine learning works, this is how science works, this is how engineering works in other disciplines. But this is how we solve the hard problems. We start and we try something, we say, oh, does that get us closer to the goal? And then we can measure it against our fitness function. It's like, no, that doesn't. That's a bad idea then, so let's stop doing that. And then we can try a different idea and see whether that moves us closer to the goal. Does that get us closer to our goal? And we can measure that, and it does, so we can keep that, and then we can keep going until we hit our goal. We can even move the goal as long as we change the fitness function when we do it, and we're going to hit the goal eventually. This is by far the most powerful way in which we can do new things, always. every time. So we should always be thinking about how we can apply that, how we can make that work in whatever context, whatever the nature of the problem that we're trying to solve. How do we break it into those small steps that we can determine that getting us closer or further from our goal? The next idea in my list of 5 is the idea of feedback. And in this example, those measurements against the fitness function are what we might think of as feedback. And part of the difficulty of software development is it's not always obvious what that fitness function should be. It should be part of our decision to decide what we should measure to figure out what gets us closer or further from the goal. But nevertheless, that's the right thing to do. So we're seeking this feedback. We're trying to figure out how we can learn. And then we're going to use that feedback to get where we want to go. I want to give you a good example. So there are 2 ways in which we could think about balancing a broom. So let's imagine that we were tasked with balancing a broom. So we could do this the waterfall way, which would be to figure out where the centre of the mass of the broom is. I kind of vaguely remember from physics that if I want to balance something, I've got to kind of position the line through the centre of mass of gravity with the point of support, and so I could orient the broom in that way and kind of calculate it. That's not right, obviously. So I could try and figure out how to do it, or rotate the broom, do something like that, and then I could very, very carefully position it so it's absolutely perfectly positioned so that that line passes through the point of contact and the centre of mass perpendicularly with respect to the gravity field and all of that kind of stuff. The problem with that, you can do that, and there are some strange people that kind of make a living of balancing odd things on top of one another and so on, because you can do this to a remarkable degree. But the problem with this is that essentially there's one possible solution to that problem. So it's a dumb way to do it. You can do it, but it's a bad way to do it. What we would all do if we were really tasked with balancing a broom is that we'd do this instead. You're already thinking about it, I'm sure. We'd get the broom, we'd put it on our hand, and we'd start wobbling our hand. We'd sense which way the broom was tilting, and we'd move our hand towards the tilt, so we could counteract the tilt. And if it tipped a long way, we could move a long way. If we were sensing very carefully, we could move a tiny way, and you have a tiny little correction, and we could keep it balanced. You could keep it. But if Goiko came up on stage and shoved me while I was balancing a broom, which he's very likely to do, then I could stagger and I could catch the broom and I could keep balancing it. So we could do that. This is a much more stable way. A feedback-driven approach to solving problems is a much more stable way. A way with many, many more solutions than just trying to answer the question perfectly in one shot. So feedback is essential to our process of learning, and so we must optimize for that. If you were to take away one thing that would have the biggest impact on your software development approach, it would be this. I would recommend that you optimize to have fast feedback on everything that you do, and figure out how to do that. It's what continuous integration is about. It's what test-driven development is about. It's what stand-up meetings and retrospectives are about. But whatever the timescale, optimize for fast, clear feedback, because you'll get a better result if you do. That feedback mechanism, that balancing mechanism, is the way that rockets fly. So what they do instead of moving a hand is that they vector the thrust at the bottom of the rocket, and they sense which way it's balancing, and they make tiny little corrections, every few milliseconds, just to keep it pointing in the way that they mean it to do. To the extent that SpaceX can now land these things. I was watching something recently. One of their rockets has landed 49 times. The same rocket has been to space and back 49 times, which is amazing. The next in my list is incremental, and incremental and iterative kind of feel similar, but they're not really. They're a little bit different. Incremental development is about modular development. It's been able to kind of grow the system through a series of steps. This is a picture of the International Space Station. It's not very familiar because it doesn't look like that anymore. It started off, that was the first bit that was put into space, and over time we added to it until it grew to look like the thing that we're kind of familiar with seeing now. My bet is that they had a rough idea that it would end up looking something like that when they started, but it wasn't exact because some of the bits that are on there now, they hadn't thought of at that time. That's one of the advantages of incremental development. It allows us to innovate and change our minds about things. It allows us to inspect and adapt. It allows us to try out ideas and reflect on them and modify them in a different way. Next in my list is the idea of working experimentally. This is all part of the same theme of optimizing for learning. And I'm a science nerd. One of my hobbies is learning about physics, which I know is strange to lots of people. So I find it alien to me when people say that they're scared of being experimental. I've had the conversation with senior people in some of my clients where I say you need to be more experimental. They say, oh, we can't afford to be experimental because we might break something. That's just, if you'll forgive me being rude, that's just bloody stupid. If you can't afford to be experimental, it means you can't afford to do anything. You can only be experimental. It's only through being experimental. Being experimental means doing things in controlled circumstances. If you're not being experimental, then you're not controlling it properly. The other thing is that you take risks. Jeff Bezos has said in the past that Amazon actively track the degree to which they're experimenting. He said a bunch of things about being experimental. He says that the risk that you take in your experiments should scale with the size of your organisation. But he's also said that they target 50% of their experiments failing, because if they're not doing that, they're not trying hard enough. Because if you think about it, if I have an idea and that idea is correct, when I execute on the idea, I haven't learned anything, because I started off with the right answer. So I haven't learnt anything. If I have an idea, the time when I learn is when my experiment fails. It's when things go wrong, and then I go, oh, that's not what I expected. Now I'm learning. Now I'm doing something new. Now I'm figuring out how to do better. So being experimental is really important to our ability to do this kind of thing. So without it, there's no way of making progress. What it takes to be able to do that is to do things like controlling the variables. We want to be clear about what the results of our experiments really mean and how we can kind of get the answers that inform our deciding which direction to take. Here's an example. Again, this is from aeroplanes. I like aeroplanes, I can't help it. There's been a very, very long history of how you make progress in aviation technology. And one of the techniques is that if you want to introduce a brand new aeroplane with a brand new engine, you don't just go and build it and fly it. That's the waterfall way, and it doesn't work. That way you kill a lot of pilots. What you do is that you do this. You have an old aeroplane, and you take the engine off, and you get the new engine, and you put that on the old aeroplane, and then a very brave person called a test pilot goes and flies it, and you see if they come back. And then you do the opposite. You get the old engine, and you put it on the new aeroplane, and another brave person goes and flies that, and you see if they come back. And if they do, and all that's okay, then you put the new engine on the new aeroplane, and you've got something new. That's how you do it. And that's been the way in which advances in aviation have happened almost from day one. It's been the way that we've tried stuff out, all the way through. So working experimentally is foundational to engineering, trying stuff out and seeing what works and keeping the things that do, and discarding the things that don't. The last of my list of 5 things is working empirically. And by this, I argued with my PhD brother-in-law over whether to include this or not, because he said it was the same as being experimental. And it kind of is. But I think in our context, this is particularly true. We have to learn from the reality of the situation. Being experimental means that we can try stuff out in theoretical terms. We can do other things as well. We can do A/B testing. We can do all sorts of interesting other kinds of experiments, and we should. But being empirical is that we need to learn from the reality of our systems. It's the unintended consequences that we're interested in, as well as the intended consequences. On the whole, if we're experimenting, We're finding out about the things that we thought of. On the whole, if we're being empirical, we're going, oh shit, didn't know that was going to happen. And we're learning from that. And that's a different kind of thing. Here's another example of being another aeroplane example. This is the first production jet aircraft. This was during the Second World War. This was a German aeroplane. This was a Heinkel. And this was the first production aeroplane to fly with a jet engine. They did the thing that I talked about. They built a version first which had a propeller on the front, and they went and flew that and tried it out, and that was all fine. And then they built this. One of the things that's interesting about this that looks a bit weird to modern eyes is that you've got two big wheels at the front and a little tiny wheel at the back. This is what's called by pilots a tail dragger aeroplane, because it kind of drags the tail along. The reason for this layout of undercarriage is to make lots of room at the front for a great big propeller, so you can have a propeller on the front and it doesn't bang into the ground when you're trying to take off. The problem with a jet aeroplane is that that means that the jet's now pointing at the ground. So that they flew this, in the first couple of flights, they melted all the runways. That's empirical learning. They hadn't thought of that, and so they changed it. Nearly every jet aeroplane that you see now and ever since this experience doesn't have the undercarriage like this. They change it round, so they have three wheels at the front. It's called a tripod undercarriage, so that the aeroplane sits in parallel with the ground, and so that the jet points away from the ground, or at least parallel to the ground, and doesn't melt the runway. Here's another example of empirical learning. This is a picture of the Starship, which Elon Musk and his crew are currently trying to build to take people, to human beings one day, to Mars. And the idea of this is to make spaceflight completely reusable. And as part of this, they're busy blowing up spacecraft because they're trying stuff out. This isn't a failure, this is a success, because they're learning from this and they're doing better every time. And they end up with something like the Falcon 9 that I showed you a picture of earlier, where there are examples of nearly 50 return journeys to space from that rocket. But that's how you get there. You have to break things along the way. You learn from your mistakes. The other aspect of software is, as I've said, it's enormously complex. The picture labeled Amazon.com is a still from an animation of the microservices that represent AWS, the Amazon services in the Amazon cloud. This is a dynamic. It's almost, when you see the animation, it almost looks like some kind of organic thing, because there are new ones appearing and others being retired all of the time. It's sort of vibrant, it's changing all of the time, and the connections are changing all of the time. These are not really understandable by human. We can't just look at that and go, oh yeah, got it. Understand that now. It's not how it works. So we need to find ways of approaching the problem, ways of thinking that allows us to deal with complexity on these kinds of scale. And it may not, your software may not be quite as complex as that. It may be, I don't know. But it's always, usually these days, more complex than one person is going to be able to hold every aspect of it in their head at the same time. That's what we do for a living. So we need to find ways to manage that complexity and constrain it in ways that allow us to do interesting things. So for that, we've got our 5 things as well. So if software development's about learning and managing complexity, what about the managing complexity bit? Well, here's my 5 things for that: modularity, cohesion, separation of concerns, abstraction, and coupling. Now, all of these, I know if you've ever written any code, if you've ever studied computer science, all of these seem a little bit motherhood and apple pie. I understand, they do. It's not quite what I mean. What I mean is that whenever you're building software, hold these in your head and try and maximize these things, always, every time, and I think you'll get a better result. So let's look at the application of those ideas. So we'll start off with modularity. Here's another aeroplane. I think this is the last of the aeroplanes. So the engine is a modular system. If the engine stops working, if the in-house entertainment system stops working, it doesn't stop the engine working. That's good, right? But they're also replaceable. You know, you can take it out for maintenance and put another one in. You could have it developed, in this case, by an entirely different company and kind of buy it and bring it in and attach it to your aeroplane. As long as you agree on the fittings of how they fit together, that's all going to work. Here's something a little bit closer to home. This is an older iPhone, but this is, despite the delicately impressive engineering and the really, every piece is engineered to fit into that little case, you know, to fit into there and have all of the pieces. Each part has a discrete function and is targeted at that function. These are modular components, and they're thought of and developed independently of the others, and we think about how they communicate and the interface between this piece and the other piece. There are contracts that we can think of, abstractions to reduce the coupling between one part and another. All of those ideas are part of the design of something like this. Here's another closer to home idea. You can tell by looking at me here in front of you on the stage that I'm quite old. I'm old enough to remember the days when, if I wanted to print something out from my software, I had to know which printer I was going to have to print out on, and I'd have to write the codes that drove that particular printer. If I wanted to print out on an Epson FX80, I couldn't use my old code from the Epson RX80. I'd have to write some new code because it was different. And then at some point, somebody came along and thought, that's stupid. Wouldn't it be better if we had some sort of abstraction of printing that we could depend upon, and then we could have a module that we could plug into our operating system that knows how to print on your printer, whatever the printer is. And now my application just needs to know, I need to print this page, here's a description of this page, and leaves all of the translation to the printer driver. And that's what happened. And now we're all used to that idea. It seems obvious. It seems really weird that you would do anything else. But trust me, we used to do other things. So this is a practical example of using the kind of modularity that I'm talking about. We can and we should be doing that in our own code all of the time and not just relying on operating system vendors and printer drivers. We should be using that kind of design technique in our own code too. Here's an example of poorly modular code. This is a piece of C that I often use to demonstrate nasty code. So the orange bit, is a single if statement, and this is 361 lines of if statement. And the most common comment that I get when I show this to people is, oh, we have functions that are much bigger than that. It's not a competition. Or at least it's not a competition that you want to win. This is what this looks like in the context of this function. And I tried to do the work for you. I tried to figure out what it is that this actually means. And I think that what this means can be replaced by this change to the code. So here's the start of the if statement, if unlikely, bang CI, and then all of this really nasty looking stuff. And I think that what the programmer meant was this. If there's no connection represented by CI, create a connection. So I changed the code to look like this. And then, looking in the context of the use of this, I found another piece of code that was almost, but not quite, the same as this, that I'm pretty sure was also using the connection. So I could have done reuse. I could have done the printer driver thing and plugged this in somewhere else and used it somewhere else. If I'd done just that change, this code would be better, right? That's always true. My favourite description of good design in code comes from Kent Beck. And it's this: good design's about moving the things that are related closer together and the things that aren't related further apart. It's kind of typical Kent Beck. It's kind of slightly funny, slightly amusing, and also profoundly true. This is exactly what good code is about. The stuff that's related should be close together. The stuff that's not related should be far apart in the code. Always do that. And we have words for these things. Things that putting the things that aren't related apart is what modularity is about. Putting things that are related together is what cohesion's about. So always do that. Always prefer code that moves the related things closer together and the unrelated things further apart into module. Always do that every time, every day, at every level of detail. Do it when you're being an architect in terms of grand schemes of subsystems and applications talking to one another and so on. And do it when you're working as a programmer in terms of single functions. Organize the things so that the variables that you're using are close together in the function and the things that you aren't are maybe in a different function. Always work like that. Because it works. Notice I haven't said anything about programming language or technology. It doesn't matter because this is always true. I'm going to come back to that idea a bit later. The next in my list is slightly different. This is the idea of separation of concerns. Separation of concerns is slightly different in that it tends to drive the other things. You get, by using the discipline of separation of concerns, that's best characterized by the phrase, one method, one thing, one function, one thing, one class, one thing. You want to try and focus your code on doing one thing and doing that thing well. And if you've got a method that's doing this and that, split it out into two methods, make it do this and the other thing separately. And you'll end up with better code when you do that. But fundamentally what separation of concerns does, it's a technique that helps you achieve more modular, better, cohesive code as a result. This is an example. This is a physical example. This is a BMW. I was just reading about the new BMW, and I haven't got a picture for you. This is a slightly older one. But this is an electric BMW. And what BMW are doing as their strategy for electrifying cars is something quite simple. They're separating concerns. And the concerns that they are separating is everything about the driving from everything about the utility of the vehicle. So what you've got is you've got this platform where the batteries are and the motors are and all of the steering and the brakes and the wheels and all of that kind of stuff. And fundamentally, they're building one of those, and then they're going to plug on top, whether you want it as an SUV or a sports car or a saloon or whatever else. And they end up having this modular system, separation of concerns, separating the practicalities of driving the car from these things. Next, abstraction. This is my favorite car. This is a picture of one of the very first cars before they'd standardized any of the parts. If you look at this carefully, there's almost no abstraction here because you can see how it all works pretty much. This thing here, this big long lever, is the accelerator and the brake in one control. You kind of push it forwards to go faster and you pull it back to go slower. This thing that looks a bit like a tiller here is a tiller. That's the steering mechanism. And if you look carefully, you can see that kind of rotates a tube and there's a little bell crank at the end that's connected to the front wheel. That's how steering works on this car. So how did that advance over time? Well, we started to abstract some of these ideas, to standardize them and to change things. So this is another steering wheel that came a bit later. Here's another one, and so on. We evolved the steering wheel incrementally over time for different reasons, and we ended up with something like this. This is a modern steering wheel from a modern car, and this is completely abstracting the problem of steering. Can anybody tell me how this steering wheel works? You can't. It might be that this is working through some kind of mechanical, maybe rack and pinion version of steering. It might be that it's power-assisted steering. It's using a hydraulic mechanism to steer the car. Or it might be, if it's very modern, it might be wholly electronic, and it's got some kind of rheostat that's measuring the voltage as you rotate this steering wheel and translating that to an instruction to an electric motor and a servo motor that moves the wheels. All of those could be true. We've entirely abstracted the problem of steering away from the driver. And that means that you don't need to care. You don't need to worry about that. You don't need to think about it unless your car breaks. Let's look at a code example of that. So here are two pieces of code, and they're talking in detail. We're going to initialize and then confirm it's been initialized. We're going to get a delivery date and return the delivery date. We're going to get some VAT, get all this stuff. We've also got this lovely little back channel that goes and looks in the private database of this thing over here, just to make sure that this never works. This is rubbish. This is a terrible way of organising a conversation between things. There's no abstraction going on here. Design is all about abstraction. What we'd much rather do is something like this. Instead of all of those very, very chatty, very, very detailed interactions between things, what would be much clearer is that we say what it is that we're trying to achieve. So we're trying to place an order, and we'd like to know when the order's been placed afterwards. Now, even if it needs all of that same stuff, the stuff is happening in one place and not both. Both places are not tightly coupled together because we've used abstraction to differentiate them. Part of the goal of good software design is to keep secrets from one part with respect to another, so we can change code in one part and not affect another part. So keeping secrets is fundamental to our ability to do a better job of design in this respect. And that is one way of tackling the arch enemy, which is coupling. So here are two examples of Lego. I promised you some Lego. When I was young, very young, I used to play with Lego like this, and I've got beautiful grandchildren, and they've got Lego like this. And they will come to me and say, "Grandpa, look." And I say, "Oh, that's wonderful. What is it?" And they'll say, "It's a giraffe." And I say, "Oh, of course it's a giraffe. It's a wonderful giraffe." Or, "It's a spaceship." "Oh, it's a brilliant spaceship." You can use your imagination. It can be anything you like. This, on the other hand, is there's nothing wrong with this. It's not evil, but it's a very, very different kind of thing. This is one particular type of car. If you wanted to build a Lamborghini out of this kit, you can't. Certainly can't build a giraffe or a spaceship. It's a Ferrari, and it goes together in one way. That might be what you want, but these are different means of coupling. These are kind of coupled because you can plug them together, but there's a kind of generic contract that allows me to plug them together any way I like. These only go together one way. So it's a very different kind of game. So here's our example. So let's imagine that we want to change the version of the date format in the orange piece of software compared to the other. In the old version, like this, that breaks at the point at which I'm returning a delivery date because these two pieces are coupled. It breaks when we try and play with the database, and so the whole system now collapses around our ears. So that's fragile. We can't change things because of those decisions in terms of design. What we could do instead is that we could do this. We could reduce the coupling by managing the change, isolating the change more clearly. Here we're kind of putting a ports and adapters kind of thing. We're going to translate the notion of date. So if somebody comes in with an old date in their place order, then we can translate that into the version 2 date. This is our internal representation. And we can translate it on the way out in response. And we could have another version of that, use the version V2 date if we wanted to. There's a whole bunch of different techniques if we manage the coupling consciously and think about that as part of our approach to design. So I'm going to run through this very quickly now because we're running out of time. You spoke too much at the start. It's not my fault. So these are the things about managing complexity. These are the techniques that we should always be doing. I'm not saying you should remember these things. You should remember these things. I know that you all know them already, but what I'm trying to say is that you should use them every day on every decision that you make. Always prefer the decision that takes you in the direction of more modularity, better cohesion, better separation of concerns, reduced coupling, and cleaner abstraction, always, in every level of decision that you make. And if you do that, I guarantee you'll get a better result in terms of your design, for one important reason, which we'll come to. So let me show you an example. Here's a car, and here's my test of that car. I'm going to create a car, I'm going to start the car, and now there's nothing that I can assert, because there's no way of me saying what's going on. I can't test that the engine should start, as I'm describing here. So that's not a very good car, because it's not testable. So one of the techniques that we can use to drive all of those better design solutions into our code is test-driven development. So if we started with a test instead, here's the test, should start a better car engine. So what is it that we want to achieve? Well, what we'd really like is that we'd like to be able to check that the engine started successfully. And so I'm going to write that down. That's what I want to happen. That means that I need an engine. I've just learned that by just writing my test. So now I want to test that when the car starts. That's the point, so I can add that. And I'm going to create my better car. And through dependency injection, I've been forced to add the engine because I need to hold on to the engine. So I'm going to create a fake engine, a better car with a fake engine. I'm going to start the car. And here's my fake engine. It's just recording the fact that the engine was started. That's all it does. So here's my better car, and all I've done was make my code more testable. That's the only thing that I've done. It was completely driven by the test. So what has that done? So it's made my code more modular, because now I've separated out the concerns of the engine and the car. Now my engine is a parameter, and it's a more abstract parameter because I've abstracted the engine. So I've improved the abstraction as well. All the engine-ness is somewhere else. All the car-ness is here. Cohesion. This stuff is all related to being a car. The stuff in the engine is all related to being the engine. There's no longer the need to create a petrol engine in this example, which there was before. So this is more cohesive code. It's more loosely coupled as a result. All of these things that I'm talking about come out as a result of applying the engineering technique of test-driven development. And we end up with something like this, as I say, it's just dependency injection, but it's dependency injection that was forced on us by our desire for more testable code. What this means the practical result of what this means is now, when I'm writing code, my better car is more useful than the old one. Because now, if I want to create a car, I can create exactly the same car as I had before with a petrol engine. That's the same as what I had before. But I can also do this. I can create a better car with an electric engine. If I'm crazy, I can create a better car with a jet engine. My code's more useful. I can use it in more ways. I can change it more easily. I can change the car-ness when I'm caring about the car. I can change the engine-ness, in this case introducing new engines, when I'm more interested in engines. This is just better code. So here are my two stacks of things. I want you to play a little game. Imagine two versions of a system. One of them, you're not iterating, you're not gathering feedback, you're not working incrementally, you're not working experimentally, you're not being empirical. Essentially, you're going to think really hard on day one, and then you're going to take however long it takes to build that thing and see if it worked. What are your chances of success compared to doing these things? I guarantee you'd rather work on the second project. Similarly, imagine some code. It's not modular, it's not cohesive, no separation of concerns, everything's in one big file, everything's confused and mixed up. Which code base would you rather work on? One like that? We even have a name for those. We call those big balls of mud or monoliths or legacy systems. But you'd prefer to work on something that was modular, cohesive, good separation of concerns with clean lines of abstraction and reduced coupling. Clearly that would be a better place to work. Clearly that would be an easier place to work. So This has said nothing at all about the choice of language or technology or framework or any of those things. All I've talked about are these kind of computer science fundamentals. So if we always write code that improves these things, if we always organise how we work it to learn more effectively, we will get better results. And we do. Interestingly, what we're finding with using AI to help us write the code is that this works when we're prompting AIs as well. If we start using test-driven development and specifying what it is that we want and working in smaller steps, that works better than otherwise. Carrying out experiments, learning from those. Fundamentally, though, all of these things matter for one reason. They allow us to change our software. So my thought that I would like to leave with you is that if you think about what quality in software means, it's this one idea. It's about the ease with which we can change it. Nothing else matters. All of these things change, so we need to be able to change it always. Move. Overdid the animation on that one, sorry. So, the quality of our system is determined by our ability to change it. Of course we want secure software, we want resilient software, we want scalable software, but how are you going to get those if you can't change the code? The only way you're going to get those is to get them perfectly right first time. Or you write it to make it easy to change and then you can evolve them over time. The second one of those is the much more durable approach to solving problems. So that's the thought that I would like to leave you with. Thank you very much. Do check out my YouTube channel. There's more on these ideas there too. Thank you very much. I hope you have a great conference.